Hey everybody, it's Mrs. Groom here. It's time to do Chapter 2 sticky notes, so make sure you have your post-it notes and a pen, and let's get going. So Chapter 2 is all about environmental systems, so we're going to start off talking about Mono Lake, which is a pretty cool story actually. It's a terminal lake in California that has a very high salt concentration on its own, like regularly. Because all the water coming down from the mountains is coming down, and as it evaporates, it leaves all the salt behind. So it's a very salty lake, and only brine shrimp and fly larvae are the only things that can live there. But it's an important ecosystem still for a lot of migrating birds. The problem is that Los Angeles diverted water from the lake, from the streams feeding the lake to their city for like drinking water and things. And what happened was as they diverted the water away from Mono Lake, it became way too salty, like even saltier, and so salty that nothing could live there, and it completely ruined the ecosystem. So no brine shrimp, no fly larvae, all the birds not coming. 50 years later, though, they've been diverting less water to Los Angeles, and they're seeing that the ecosystem is slowly recovering. So this is a good example of a system, as Mono Lake is a terminal lake. Okay. So environmental scientists study systems, and really the biggest system that environmental scientists study is the Earth. It's the largest system, and the two big things that move within the system are energy and matter, and we'll talk about each of those kind of separately. So a lot of this chapter is going to be review from what you should have learned in biology and chemistry and physical science. So I'll kind of tell you, I'll hit on the basics, but you definitely need to read through all of this. So for this first part, it's bio and chemistry review. So we're talking about matter. So we're talking about the fact that matter is part of Earth's system. Matter is anything that has mass and takes up space. And so, and remember the kind of progression of an atom to an element to a molecule to a compound, and then those come together to make larger compounds, which then make organelles and cells and all of that. So you need to have a good understanding of the difference between atom, element, molecule, and compound, and know the basics of the periodic table as far as what the periodic table can tell you. All right, page 30. So continue to kind of learning about mass number and things like that, but then it's going to switch over to talking about isotopes, which are atoms with different number of neutrons, and this definitely comes into play when we talk about nuclear energy. But special type of isotopes called radioactive isotopes are unstable, and they decay, and they have a known half-life, which is the amount of time it takes for half of the radioactive isotope to decay. And so they can use that to date things and to figure out how old fossils or rocks or anything might be. Okay, continuing on with kind of the biology chemistry review on page 31. Talks about the three different types of chemical bonds: covalent, ionic, and hydrogen. So you need to remember the difference between these three and examples of things that use those types of bonds. All right, page 32. This focuses on properties of water, and there's a lot, and water is super important. Water is a polar molecule, which means it has an uneven distribution of charge. It's got a negative end and positive ends, and that plays into basically everything else. Water exhibits cohesion, which is when water molecules stick to each other, and that provides what's called surface tension, which allows like a bug to walk on water or something. Adhesion is the ability of water molecules to stick to other things, and that leads to capillary action, which is the movement of water molecules like up a tree trunk or up a tube, and so that's super important. the thing about water too is that it does not undergo big temperature shifts. It really takes a lot and a long time to make water change its temperature greatly, and so it helps to keep the water stable as well as the adjacent land to keep it at somewhat of a stable temp. All right, page 33. Remember that water takes up more volume as a solid rather than a liquid, which is very odd compared to most other things, and that ice floats on water. But the good thing about that is that it helps to prevent lakes and ponds from freezing on the bottom. So it doesn't freeze from the bottom up, it freezes kind of from the top down, which allows a lot of living things to still live in water, lakes and ponds, even in the wintertime. And then remembering that water is a universal solvent, which means it dissolves most things, or most things dissolve well in water. Okay, and then we kind of focus on the pH scale for a little bit, and this will be definitely important as we'll be testing lots of things for pH. Remember that the pH scale from 0 to 14, okay, 0 to 14, from above 7 is base and below 7 is acidic, and bases are the type of solutions that release a lot of OH negative ions into solution. Acidic solutions release a lot of hydrogen ions, H pluses. And do note that this is a logarithmic kind of scale, so from 6 to 7 it's actually a factor of 10. So it's going to be times 10 times 10 times 10. So the number's a little bit bigger than just 1. Okay. Good old chemistry here, talking about chemical reactions and the fact that you've got to remember the law of conservation of matter, the fact that what goes into a chemical equation must come out. So the number of atoms or molecules that go in on the left side have to be the same as what comes out on the right. And this is based on the law of conservation of matter, that matter is neither created nor destroyed, it can just change its form. Okay, then we switch over to some biology, which of course I like a lot. And this is where the molecules and compounds come together, start making larger molecules. Remember that inorganic means it's a compound or a molecule that does not have carbon with hydrogens. So it still might have carbon like CO2, but it doesn't have carbon and hydrogens together. Organic means it's carbons and hydrogens together. So the 4 major types of biological molecules: carbs, proteins, nucleic acids, and lipids. So take a look at those 4, make sure you're familiar with the basics of each of these 4 types of molecules, examples of each. And then of course these come together to make cells, which we all know cells are make up all living things. All right, so that ends the kind of biology, chemistry, looking at matter. Now we're going to switch over to look at energy, and that would be physical science type of review. So some of you may not have taken physics, and that's okay, but you've had physical science throughout your life. And so you may need to read this part a little bit more just because it may be a little not as fresh. So physics is the study of energy. Energy is the ability to do work, and it's measured in joules. Power is the rate at which work is done, and that is measured in watts. So when we do our energy unit, this is all going to come back. Okay, you need basic understanding of the electromagnetic spectrum and the different wavelengths, and the fact that shorter wavelengths have higher energy, longer wavelengths have lower energy. And then there's the visible light and the infrared and the UV, which is what we mostly get from the sun. So then looking at some more units, we have a kilowatt is a unit of power. So that shows the rate at which energy or work is done. But a kilowatt hour is a unit of energy, because that is how much work is being done, and it's already given a time. So you'll see this a lot, kilowatt hour. Then there's two major forms of energy, and that would be potential and kinetic. Potential energy is stored energy, so it's energy that's kind of waiting to be used, and kinetic energy is the energy of motion. So any kind of movement is going to be showing kinetic energy. Systems contain potential energy, kinetic energy, or some of both, and it kind of depends on what's happening, but it tends to show both. Okay, we are not going to worry about this math right now, not very hardcore, okay? So we will learn about this more when we look at that particular unit on energy. All right, let's switch over to looking at the laws of thermodynamics. So the first law of thermodynamics says that energy is neither created nor destroyed, can only change forms. It sounds very much like the law of conservation of matter. So first law, energy is neither created nor destroyed, it can only change forms. And then that leads into the second law. So the second law of thermodynamics says that when energy is transformed, some energy is lost, and it's usually by heat most of the time, sometimes by sound. Also, entropy is always increasing. Now, entropy is that like disorder. And so this law definitely comes into effect when we look at how efficient different things are. So this is a good figure here to know conservation of energy within a system. It shows the energy inputs and outputs, the fact that what you put in, potential energy that you put in, which is chemical energy is gasoline, will become kinetic energy, which will move the car, but at the same time some of the energy is lost as heat from friction, and then sound from even just the tires on the road surface. Okay, so here we're going to, on page 40 and 41, page 40 and 41 is looking at energy efficiency and energy quality. So for energy efficiency over on page 40, it's talking about more efficient machines get rid of or lose less heat, lose less energy. So the more energy it can actually keep in the system and use to do what it needs to do, the more efficient it is. And energy quality, so if it's a high quality energy source, something like gasoline, it's easily it's concentrated, it's convenient, it's easy to carry around, versus low quality energy source, which would be something like wood, and it doesn't give you as much bang for your buck. So those are two important terms. Okay. So when we talk about energy conversions, because we know that energy can just switch from one form to the other, page 42, that the amount of available energy determines which organisms can live in a natural system. So for example, there are no plants in the deep ocean because the sunlight does not get that far down, and so there's no photosynthesis. So the amount of energy available to that system determines what can live there. So that's just one example. All right, so now let's talk about the systems and the fact that we know environmental science is the study of systems. And a couple of vocab terms: open system, closed system, inputs and outputs. Inputs is what goes into a system, outputs is what goes out. Open system means that the thing factors can come in and out kind of freely, but a closed system is one that is closed to any kind of inputs and outputs. So this figure on page 43 is a really good one. It's looking at the Earth as our biggest system, and the fact that it is an open system when it comes to energy because the solar radiation is coming in, and the outputs would be the heat and energy reflected. And then, but the Earth is actually a closed system for matter. So all the matter that's been on Earth has been on the Earth since like the beginning of Earth, which is kind of cool to think about. So then we kind of skip over to read 44, 45. 44 talks about steady state, and steady state is the idea that a system is steady so that the inputs equal the outputs, and generally that's kind of like what it's aiming for. But now we have to look at feedback loops, because a lot of times there are changes that occur in a system and adjustments have to be made. And this feedback loop would be basically the system's response to that change and how it's going to act based on what happens. So there are two types of feedback loops. There's the negative feedback loops, and negative doesn't mean bad. Negative means that it resists the change. So the system is going to resist whatever change, or you'll just see no change at all. And there are other really good examples too, like predator prey. So this is a good figure down here though to show examples of both negative and positive loops. And then finally, to end up, talking about positive feedback loops. This would be if a change happens in a system and the system amplifies that change or makes that change increase. Doesn't necessarily mean a good thing. But the health of many environmental systems depends on feedback loops. So this is happening naturally. Of course, there's natural things or anthropogenic factors that can affect ecosystems and cause them to have to change. So they either would do these kind of negative or positive feedback loops. All right, and then just kind of finish reading up the chapter, and that is it for chapter 2.